Okay, one of the cool things about this course is that we start way down at the transistor level and talk about how to build gates out of transistors. And then once we have gates, we can move on up the abstraction levels to where we do some pretty cool things with digital logic. All right, so let's start with a CMOS inverter gate. Okay, so this is a schematic that you'll see of that. Up here is a PMOS transistor. This is an NMOS transistor. The difference between the two is the bubble at the gate here. There's a bubble on this gate that indicates that a low voltage will actually make this gate conduct. So in this infographic, this is showing this conducting. Now, one of the things that confused me when I was learning about transistor circuits is, where's the current flowing to? I was used to seeing a circuit loop, and that loop is still there, but in these type of diagrams, we abstract that away. So let me put the loop back in for this case. So here is a voltage supply that's connected to VDD. This is actually a wire, okay? And so because this transistor is conducting, this goes on through to the output, and typically this would be connected to some other load, like maybe it would be another gate. So because this is connected to VDD, all right, this output level is a high voltage, okay, and current would actually flow through here. Now, because this was a low, that's what turned this on. Look what happens when we turn this to a high voltage, okay? With a high voltage, the bubble here means that you take a high voltage, hit the bubble, it's like a low voltage, and it turns this off. So this PMOS transistor is turned off, and there's no connection between VDD and the output here. On the other hand, the high voltage, now there's no voltage drop across a wire, so the high voltage goes to the input of this NMOS gate, which turns it on. All right, so when that turns that on, that grounds the output, so the output voltage is 0, and there would literally be no current flowing in that particular circuit. So that's the idea of how an inverter works. Let me turn this back off. This is the schematic that you would typically see. Once more, to go through the logic here, when you have a high voltage, this transistor is on and it connects the output to ground. When you have a low voltage, this transistor, because of the bubble, this transistor is on and conducting, and it makes this connection to V out. So V out would be connected to VDD, which would be a high voltage. Before we move on, I want to talk about this structure here. So you have an output, and you're either going to pull the output down to ground or up to VDD, depending on the logic that we're trying to implement. So with an inverter, the logic is pretty simple. We want the output function, F, to be A bar. Whatever A is, we want to invert that. So if A is a high, we want it to be a low. If A is a low, we want it to be a high. All right, that's what happens on the pull-up side, and that's what the bubble gives you. The bubble gives you that inversion. But on the low side, what we're actually trying to do is pull V out down. So essentially, we're trying to make F bar equal to A. So the complementary logic condition is what we're going for on the pull down circuit. So if I put F bar equal to A, notice what comes into this. This is just A, the input A coming in to the pull down network. All right. So that's an explanation of how a CMOS inverter circuit works. Okay, the next gate that I wanted to walk you through is the CMOS NAND gate. Okay, so NAND means not and so if you look at the truth table here, here is the input combinations for A and B. If this were and, it would be 0, 0, 0, 1. So you can see it's the opposite of that. So let's walk through why that would be the case with this particular transistor configuration. So what you should notice here is that on the output side, where we're trying to make V out drive up to VDD, so right here on the pull-up side, V out is equal to F, which is the NAND function. So the NAND function is a B with a bar over the top. And later on, you'll learn that this is by De Morgan's theorem, equivalent to A bar or B bar. All right, so notice that when you have this path from VDD to here, you can go this way or you can go this way. Because it's OR, you can go either way. So like if this were cut off because this transistor is off, you still have this path. And conversely, if this one were cut off, you would still have this path. So these bubbles mean here's A, that's A bar. All right, here's B, that's coming up to B bar. So the pull-up side is A bar or B bar, which, like I said, is equivalent to NAND. All right, so let's talk about the only way that you can get this to go low. All right, the only way to get this to go low is to shut off both A bar and B bar. So in other words, make them both high. So when they both go high, we go to this logic. Okay, so this logic is the pull down network. And if I look over here, the pull down network is F bar, which if you take the complement of A ended with B bar, you just get A ended with B. So both of these things have to be on. A has to be on and B has to be on for current or for the connection to be made between V out and ground. Okay, so play around with this. You can see the transistors turning on. When I turn this on, that gives us a path for a connection to VDD. When I turn it off and both of these are high, you have the connection back to ground. When you trace through all the combinations, this gives you the NAND function. And the last gate configuration that I wanted to cover in this section is the NOR gate. Okay, so NOR means A or B with a bar over it, so not OR. All right, so if you take a look at this truth table, if you go through all the input combinations, OR would be 0, 1, 1, 1. And so if I flip all those bits, I get NOR, which is 1, 0, 0, 0. All right, so looking at this configuration, we can see that the pull-up side, all right, we're trying to implement NOR, which is A or B with a bar over the top. If you applied De Morgan's, that would be A bar ANDed with B bar. So when you put things together in series with the transistor, that means this path, both these transistors have to be on for this to be connected to V out. So that's how the pull-up works. Remember, the bubbles mean that's A bar. The bubble here mean that's B bar. Okay, so if I have A bar ANDed with B bar, both those true, you have a connection to V out. Okay, on the pull down side, you take the complement of F bar. All right, so we have A or B. There's a bar over the top. When you take the complement, the bar goes away and you just have A or B. Well, A or B suggest parallel paths, okay? And so if I change one of these to high, notice what happens. One of these transistors on the lower half of the circuit, because this is connected to A, so when A is equal to a high, this transistor is on and we have a path to ground. Okay, so the output would be a 0. So it turns out if either one of them are high, we have a path to ground. We can tell that by the structure of the parallel paths with the circuit. Okay, so this function, if you go through all the combinations, I urge you to try that. 0, 0 gives you a 1. Okay, go through the rest of these. Any other combination will connect you back to ground. So this is a NOR gate.